Welcome to the lecture series of signals and systems. In the last lecture, we completed some important properties of the Laplace transform, and we are left with some two or three more properties of the Laplace transform we will cover in this lecture, and then we will discuss some examples to clarify the properties of the Laplace transform more. So the remaining properties are it is Parseval's theorem and initial and final value theorems of the Laplace transform. The Parseval's theorem states that properties Parseval's theorem or property or we can call it Parseval's relation, which states that if the Laplace transform of x of t x1 of t is x1 of s and Laplace transform of x2 of t is x2 of s, then the Laplace transform of, or we can directly write it as integration of x1t into x2 star or x2 conjugate t dt, where limit is from minus infinite to plus infinite, will be equal to x integration limit is from minus infinite to plus infinite, or also we can write limit here from sigma minus j infinite to sigma plus j infinite x2 conjugate of minus s conjugate ds. This is what the Parseval's relation states, that the integration of x1t into x2t limit from minus infinite to plus infinite is equal to integration sigma minus j omega to sigma plus j infinite x1 of s x2 of conjugate of minus s conjugate ds. Also, obviously we have to divide in this relation with 2 pi j. How we can prove this? Proof. We know that the Laplace transform of the signal xt is equal to integration from minus infinite to plus infinite x of t e to the power minus st dt. So similarly, the Laplace transform of this signal x1t into x2 conjugate t will be equal to minus infinite to plus infinite limit x1t into x2 conjugate t into e power minus st dt. This is what we can find by using the relation of the Laplace transform. Now, we know that by using the inverse Laplace transform relation, we can write one of the signals. Suppose I am writing x1t as inverse Laplace transform of x1 of s, and inverse Laplace transform of x1 of s can be written as 1 upon 2 pi j limit sigma minus j infinite sigma plus j infinite x1 of s into e power plus st ds. This is how we can find the signal x1t back from the x1 of s. So now I will put this value of x1 of t in place of this here. So after putting the value of x1 of t in the relation, we will get we does not have to use this relation in this. Directly I can write the Laplace transform of. So because x1 is Laplace inverse of the x1 s gives x1 t. So this relation in the Pascal's theorem that x1 of t into x2 conjugate t dt can be written as, from here I will put in place of x1 t I will put this relation, so this will become 1 upon 2 pi. First of all I will write minus infinite plus infinite this limit, then value of x1 of t which is equal to 1 upon 2 pi j, 1 upon 2 pi j integration sigma minus j infinite to sigma plus j infinite x1 of s e to the power plus st ds, and remaining is x2 conjugate, this is value of x1 into x2 conjugate of t dt. From here we can change the order of integration as, we can change the order of integration as, so this will become from here 1 upon 2 pi j integration from minus infinite to plus infinite. I will put x1 of s here and integration sigma minus j infinite to sigma plus j infinite. I will put x2 conjugate of t into e power plus st dt, and with this will be integrated with respect to ds. Now we can find from here that this can be written as 1 upon 2 pi j limit from minus infinite to plus infinite x1 of s into, this can be written as limit sigma minus j infinite to sigma plus j infinite. Now instead of writing x2 conjugate t, I will write it as x2 t into e power s conjugate t dt with whole conjugate into ds. Because when this will come inside, I will conjugate both of them, x conjugate t into s conjugate of conjugate, this will become s again. So I will write this term x2 conjugate t into e power st dt, we can write it in this way, x2 of t e power s conjugate t whole conjugate of this. So this can be further simplified as 1 upon 2 pi j minus infinite to plus infinite, limit here is x1 of s, x1 of s, this is integration sigma minus j infinite to sigma plus j infinite x2 of t into e power minus of minus s conjugate t dt, and whole integration with respect to ds. So purpose of writing here 2 minus is simply to compare this relation with the standard form of the Fourier transform, that this x2 of s can be written as x2 of s can be written as integration minus infinite to plus infinite x2 of t into e power minus st dt. Simply, so it is not visible. Let me write here. This relation can be compared with x2 of s can be written as limit from minus infinite to plus infinite x2 of t e power minus st dt. But in place of minus s here it is minus, in place of s it is written here minus s conjugate. That is the difference. So if it is the value of x2 of s, then what will be the value of this integration? This will be equal to x2 of this whole integration will be equal to x2 of minus s conjugate. So this whole relation can be written as integration from minus infinite to plus infinite x1 of t into x2 conjugate of t dt will be equal to integration, this integration will remain as it is 1 upon 2 pi j integration from minus infinite to plus infinite. This is x1 of s and this is x2 of minus s conjugate ds. This is what the Parseval's relation states, that if the Laplace transform of x1 of t is x1 of s, the Laplace transform of x2 of t is x2 of s, then the Laplace transform of x1 of t, then the integration of x1 of t into x2 conjugate of t will be equal to 1 upon 2 pi j limit minus infinite to plus infinite x1 of s into x2 of minus s conjugate ds. And the remaining properties of the Laplace transform is, one is the initial value theorem. Initial value theorem states that if the Laplace transform of x of t is equal to capital X of s, then limit t tends to 0, x of t will be equal to limit s tends to infinite s into capital X of s. This is what the initial value theorem states. To get the initial value of function means when at t equal to 0, value of xt at t equal to 0. This is what the initial value theorem states. We can find the proof here. Suppose it is given here x of Laplace transform of x of t is equal to x of s, then Laplace transform of d by dt of x of t will be equal to integration from 0 to infinite d by dt of xt into e power minus st dt is equal to Laplace transform of d by dt of xt will be equal to s times x of s minus x of 0 from the time differentiation property of the Laplace transform. From the time differentiation property of the Laplace transform, if we differentiate the signal in the t domain, then in the s domain we will get the function s into x of s minus x of 0. Now apply the limit t tends to uh, write it as limit s tends to infinite on both sides. So this will become limit s tends to infinite integration from 0 to infinite d by dt of x of t into e power minus st dt is equal to limit s tends to infinite s times x of s minus x of 0. Now put the value of limits here. Putting the After putting the value of limits, when this s will tend to infinite, when this s will tend to infinite, this will become 0. It means that this side of the equation will become 0 and we will put the value of limit. So this will become 0 is equal to limit s tends to infinite s into x of s minus x of 0. And now this will become x of 0 is equal to x of 0 is equal to limit s tends to infinite s times x of s. This is what the initial value theorem states. Means to get the value of the function at t equal to 0, we can also find the initial value of the function by multiplying with s in its Laplace transform where s tends to infinite. By using this relation, we can find the initial value of any given function. Another similar property is the final value theorem. Final value theorem of the Laplace transform states that it is final value theorem. Final value theorem of the Laplace transform states that if the x of t has its Laplace transform as x of s, then limit t tends to infinite x of t, or we can write it as x of infinite, will be equal to limit s tends to 0 s times x of s. This is what the final value theorem states. In the same way as we have seen in the initial value theorem, we can find the proof for the final value theorem as we know that Laplace transform of d by dt of x of t will be equal to its Laplace transform as sigma integration from minus infinite to plus infinite d by dt of xt into e power minus st dt. And by using the time differentiation property of the Laplace transform, by using time differentiation property of the Laplace transform, we can write it as s times x of s minus x of 0. Apply limit t tends to infinite, sorry, limit t tends to 0 on both sides. When we will apply limit t tends to 0 on both sides, this will become limit t, sorry, this is s tends to 0. I will apply limit s tends to 0, integration from minus infinite to plus infinite d by dt of x of t into e power minus st dt is equal to limit s tends to 0 s into x of s minus x of 0. Putting the value of limit, when I will put s equal to 0 here, this will become e power 0, means this will become 1. So integration from minus infinite to plus infinite d by dt of x of t, d by dt of x of t into dt is equal to limit, remove the limit here, this will become limit s tends to 0, it is s times x of s, and this term is not dependent over s, so I will write it directly as minus x of 0. Now if xt is a causal sequence here, I will determine the limit of this integration from 0 to infinite. So this is integration of differentiation of xt. So this will directly become x of t, and limit on the x of t will be from 0 to infinite. So this will become x of t, and limit on the x of t will be from 0 to infinite will be equal to limit s tends to 0 s into x of s minus x of 0. Now put the value of limit here, this will become x of infinite minus x of 0 is equal to limit s tends to, it is 0 here, limit s tends to 0 s times x of s minus x of 0. So this will cancel, and x of infinite, or we can write it as limit t tends to infinite x of t will be equal to limit s tends 0 s tends 0 s into x of s. This is what the final value theorem of the Laplace transform states, that to get the final value, to get the final value of an equation, we have to just multiply in the Laplace transform of this signal with s, and we have to put the limit s tends to 0. This is the final value theorem of the Laplace transform. Now we will consider some examples in which we will include the examples on the initial and final value also. The first given example is first I will consider the same example which included in the last lecture. Two part of that examples are left. So first I will consider this example in which x of s is given as s plus 1 upon x of s is given as s plus 1 upon s square plus 3s plus 4. X of s is given as x of s plus 1 upon s square plus 3s plus 4. This is the Laplace transform of the signal x. This is the Laplace transform of the signal x. And we have to find the value of x of 2t as we determined in the previous lecture. Value of t times x of t determined in the previous lecture. The remaining parts are we have to get the value of e power minus 2t x of t, e power minus 2t x of t, and the last part was, this was the third part, the last part was x of t convolution with x of t. This is what we have to calculate, and Laplace transform of the xt is given in the question itself. So this is the shifting property of shifting in S domain of the Laplace transform. Shifting in S domain says that if the Laplace transform of x of t is x of s, then Laplace transform of e power minus 2t x of t will be equal to x of s plus 2. This is the shifting in S domain property of the Laplace transform. In the given equation, x of s is given here. So x of s is given here as s plus 1 upon s square plus 3s plus 4. Then s, if we will multiply with e power minus 2t, so this will become x of s plus 2, and in place of s now I will put here s plus 2. So this will become s plus 3 upon s plus 2 square plus 3 times s plus 2 plus 4. You can simplify it further as s plus 3 upon, this is s square plus 2s plus 4 plus 3s plus 6 plus 4, or this can be further written as s plus 3 upon s square plus 2s plus 3s. This will become 6s plus this 6 plus 4 and 4 plus 14. This will be the value of Laplace transform of e power minus 2t into x of t, shifting in the s domain property. Now consider the next case which says that we have to, the Laplace transform of xt is known, we have to get the Laplace transform of convolution of xt with xt. Laplace transform of convolution of x of t with x of t. And we know that convolution in the time domain will lead to multiplication in the S domain. So this will become x1s into x2s, and in place of x1 it is x of s, in place of x2 it is x of s. Simply it means that we have to make a square of given Laplace transform. That will be equal to whole square of s plus 1 divided by s square plus ps plus 4 and whole square of. This is what the this is how we can apply the convolution property of the Laplace transform to get the Laplace transform of the convolution of two segments. So this is all for this lecture. In the next lecture we will include some more important examples related to the properties of the Laplace transform, including initial and final value theorems of the Laplace transform. So this is all for today. Thank you.